Okay. So this presentation is going to be about sensing and big data analytics for natural disaster management. So the outline of this presentation is we're going to be talking about natural disaster management in general, then we're going to focus on the technological concepts and objectives that we might, and the technical objectives that we might have during the natural disaster management scenario. Then we're going to go through some natural disaster management sensors, and afterwards we will be diving into how we use those sensors to devise, extract big data analytics. All of this presentation is part of our research project. Okay. So natural disaster management examples would include forest fires or floods. In particular, in this demo project, we are focusing mostly on forest fires and floods. So, of course, there are other natural disasters like earthquakes. And one of the biggest issues in natural disaster management is that we need mapping and phenomenon evolution prediction in real time. To this end, we can use heterogeneous extreme data sources like AI-capable autonomous devices and smart sensors installed at the edge. You can also use satellite images, topographical data, visual meteorological data, and prediction warnings published in the web. And of course, we have the issue of multilinguality, especially when we are analyzing geo-social media. That would include social media posts, including text, image, and video. So this is an overview of the natural disaster management scenario. So we have multiple input data sources that all need to arrive and controlled by a command center. So you want to devise a tool that is able to collect information from many different modalities, combine them into one map, and help the natural disaster response authorities make the right decisions and understand the situation. So more specifically, in the demo project, we have the concept of multiple data sources arriving So multiple data sources arriving from, we see the rectangle on the left, that would mean drone data, smart sensor data, social media data, etc. And they are arriving through modeling and an analytics module to extract information. So the analytics module, let's say, receives one image and localizes the file. Then another tool localizes the file in the 3D space. We also have the modeling tools that could be from this localization of the file in the 3D space. We can run some fire simulation to see how the phenomenon could evolve in the future. And then we also need an interactive visualization module that could take all those inputs from those analytics and modeling tools and show them in an intuitive and interactive way to the natural disaster management response authority. And then the response planning and documentation module would analyze all the data sources, including the decisions of the natural disaster management authorities, and propose maybe different response plans. And all these modules will be tested and are currently being tested in pilot trials, in real case studies, taking into account ethics, human factors, and etc. So the overall objective is to improve and accelerate. So the objective of the analytics model is to improve and accelerate data analytics. More specifically, to increase the trustworthiness of analytics algorithms, the accuracy of different tools, the responsiveness, speed of the algorithms, and the overall latency by using a federated data analysis, combining edge and cloud continuum. So, for instance, some analytics could be fire detections, fire segmentations, LiDAR and maps, social media analysis, and etc. Then we also have the objective of improving natural disaster prediction tools for understanding evolving phenomena, such as fire simulation and flood simulation. We have partnered with specialized industrial partners that have developed tools for simulation and visualization of such phenomena. Then another objective would be to improve the responsiveness and interactivity of visualization mechanisms for evolving phenomena, including content customization and augmented reality versions. And of course, the accuracy of digital tools. So, such as example, in the slides we see a couple of examples of actual natural disasters that took place in Greece in 2023. And the overall objective of combining all the tools together is to reduce latency and natural disaster management in general. So, if we have the analysis of multiple data sources fast enough, then we can say that the situational awareness increased. Then we have the tools that analyze all those sensor data and provide response recommendations. So overall, this reduces the mental load for human operators. And this is all performed by building a prototype proof of concept system. Okay, so this is an example of such a system. Now, we'll be talking about what types of sensors can be used in a natural disaster management system. So, one example is obviously ocular images or stereo images, calibrated or not, event cameras. They are similar to RGB cameras, but they are more responsive. They have some advantages. There's no problem of motion blur because they can capture data really fast. And they also have a huge dynamic range, so they don't have issues with dynamic range caused by facing the sun, etc. So this is a video. Fortunately, it's not a video, but I will show you what the output would look like. And of course, we have LiDAR sensors. Those employ laser illumination and measure the reflected light with the sensor. The overall output is a 3D voxel space representation of objects, activity. Then we have IR cameras, which produce thermal images of an object that measures the radiant heat. And of course, in natural disaster management scenarios, they are very useful because they can detect fires in the earliest possible stage. So this is an example of some industrial grade fire detection system that would include stereo cameras, thermal cameras, processor that analyzes those images, localizes them. We can also integrate smoke detectors. Those are useful to, of course, understand the situation of the fire better. And they also sometimes are combined with wind sensors. And LiDAR can also be used for smoke detection. And then we have the meteorological sensors, which determine wind speed, direction, and temperature. And an example drone of natural disaster observation would include some of those sensors. Like this particular drone has LiDAR, it has stereo cameras. So those are very useful. And XR camera also, those are very useful for fire detection. So this particular is a visual camera combined with a thermal camera and the laser rangefinder. So this type of sensor is also a RGB camera, including a thermal sensor. So I'm not going to put everything. Okay, so now we will be seeing some example data analytics that arrive by analyzing those sensors. Of course, all of them have some underlying neural networks and computer vision technologies for object detection, region segmentation. So one example is the fire segmentation, which can be performed in real time by analyzing RGB and IR images using lightweight deep neural networks that are deployed on the edge. And with the term edge, we might mean either on the embedded hardware, drone hardware, or on a computer that is very close to the drone. So the drone transmits those images to a local computer, and the fire segmentation is performed in that computer. So that the edge devices. Of course, this can also be done in the cloud, but the later in the pathway, the biggest layers. Then we have satellite data analysis. So this is mostly performed on the cloud. The problem with satellite data analysis is that it takes a few hours for here. So they're not very good for detecting the first point of fire, but they are very useful to see the inflicted area and predict also which buildings are around fire and so you can use them to devise analytics about the fire, the understanding of the situation. Then you need some algorithms to reference burned regions with regions that were there before, some natural disaster models, so you can measure what has been damaged. And it's not very trivial to do if you don't use the exact same flight. Then there are tools that take as input. As I said, the initial starting point of fire, this would be a point in the 3D space, and then use the weather forecast and also sensors placed around an afflicted area so it can get improved, let's say, meteorological accuracy of the situation, because fires are very are well known that they cause their own climate, their own microclimate, so you probably need sensors very close to the fire to understand how the fire might go, and such tools can provide accurate predictions for up to 8 hours, if I'm not wrong. And then we have the flood case. So in floods, the constraints are a little bit different than the fire scenario. Type of different sensors, so infrared is not used to detect the starting point of a fire, but it can be used to detect potentially people that are trapped inside a flooded zone. So the first step is to identify the size of the inflicted area, and to this end, flood segmentation algorithms can be used with UAVs if you need some fast determination of this area, or the satellite analysis can also be used. And drone data are very useful to detect cars or people inside some flood zone. And if you want to have a better overview of the situation, such that satellite data analysis is very useful. So this particular case, the DLR Institute from Germany used the Copernicus data to perform satellite data analysis of floods inflicted in different European cities. So they can extract the flood extent, flood duration, and also physicals around an area. And buildings. So this is an example I'll put in the flooded zone by combining satellite and aerial images for doing building and vehicle detection. Then the phenomena of the flood can be simulated using some hydrodynamic simulation software. We have a specialized partner that is from the Netherlands, called Schuurmans. They work in flood modeling in urban or suburban areas, and they can do a projection of the simulation to two-dimensional map. Then we also have a specialized partner that can do 3D reconstruction of an inflicted area. So as you can see, what's on the top is if you use 3D modeling using standard algorithms, and for our partner in Northwoods, if they do the 3D reconstruction, it looks more visually appealing. And then we also have other visualization tools that are more targeted to the natural disaster management response authorities. So this is the smartest tool developed by our Finnish partner from the University of Applied Science in Kajaani. And so the smart disk is both hardware and software solution. features a table, and this table is a computer with all the cables integrated and the screen, etc. And it's a big touch screen, very nice to use in an actual natural disaster management scenario from a response authority. And it also has a software part that visualizes the output of the flood simulation, the fire simulation, the analytics, the 3D maps, the fusion of the information, and also the social media analytics and localization. Then we have the geosocial media analytics, and we are working on understanding and so what's the main problem in geosocial media analytics? So someone might post something about some specific event from anywhere here. So you need to filter out social media posts based on relevance to the actual event, and you also need to filter out maybe perhaps on based on the localization in the 3D map. So if someone is talking about a flood in Larry Islands and they are located in the USA, maybe it's not that relevant. So using those analytics, they can extract hotspots from by phone. So they can extract hotspots, and those hotspots can be also used to trigger a natural disaster management response system, such as TEMA. So let's say someone posts that they saw a fire outside of their window, and then you can send the drones there to check if there is actually some fire. So the social media posts are maybe the least accurate in terms of localization, but they are the fastest in terms of information flow. And then when we have all those multiple data sources, like elevation maps from we have collected from all the world. In some cases, we have drones for sensing, we have simulators, we have data analysis, we have social media analysis, and we need to fuse all those all this type of information to understand which of this is more reliable and can be projected in the system. So this information fusion algorithm is developed by our partner with University of Seville. And finally, we have a partner that is doing an explainability analysis of sensor output. So, as I said before, most sensor data are fed into neural networks, and neural networks, they are extracting those analytics. And the explainability algorithms are trying to see what did the neural network actually saw for devising this prediction. So it's a very useful addition that brings extra robustness and trustworthiness for a natural disaster management system. So another use case of explainability is to have a neural network that takes multimodal inputs, like so you have smoke and fire segmentation using infrared and RGB sensors, and maybe you trust more the analysis of the infrared sensor because it's more expensive and more sensitive to detecting fire and smoke and so. But judging from the network output, you don't know which modality was more useful for doing the prediction. So the explainability modules are able to extract some additional insights that are very useful. Then we also need technologies for person re-identification. This technology is because, let's say, in a flooded zone, you detect multiple people, and someone then asks if some missing person has been detected by the drone. So the re-identification algorithm create a table of different people, person IDs, so can be matched to some missing person ID. The detection algorithms might detect people, but they don't know if they are detecting the same, the same person again and again. So such tools are useful to summarize the analytics outputs of the detection algorithms. And then, since we might be recording humans, privacy protection algorithms are very useful. So the overall pipeline would be first perform some face detection or face recognition, and then apply a layering algorithm for a complete blackening of the face. Of course, more recent methods based on neural networks can generate from unperceivable to very high noisy examples. And the good thing with neural network approaches is that they are designed to make sure that the faces cannot be identified by a neural network, while blurring that the human might do, so that guarantee that the neural network will not be able to identify that person. So all the results that I have presented to you originate from the TEMA project, which is a European project that features 19 partners all over Europe, and it's coordinated by the Aristotle University of Thessaloniki. And much of the material provided to this presentation was provided by TEMA partners. And